Well, hello friends. Today we're going to try to build a kernel module, and we've never done that before, so this will be new territory. But I think it's a feature that will be really good to have because it will allow us to do stuff like optional drivers and optional features in the kernel. So the basic idea that I have is we would have a command that you give it like an object file, and it will just load that into the kernel address space somehow, and sort of relocate everything on the fly and link any symbols to kernel symbols based on I don't know, like the kernel symbol table. So I don't know how this is going to work. We'll figure it out somehow. So I guess the easiest way to do this is to just have something that we build as part of the regular kernel build process, but we don't link it into the kernel. So it's like this thing that we can link in later. And then we also give it like some special named function that we call after we load it into the memory. Then we just call that function. So that's like your initialization function or construction function or whatever. And then we should probably have one for uninstalling a module too. But right now we're just going to focus on installing a module. So I think let's just for simplicity, let's just make a directory here called like modules. Or maybe they shouldn't be in a directory called modules. Maybe they should just be sitting around with everything else. Okay, test. We'll have one called test module. Test module .cpp. Save that, and when we build, let's see. Okay, so we'll just, this is the all of the object files right now are here, but we'll make a separate one. So we'll make one called module objects, and we'll put this right here, test module.o, and then we'll make sure that this goes. Let's see, let's call this one kernel objects, and then we'll have, or no, hold on, let's see how this is used. Objects. So the kernel is built from all the objects, but we don't want this particular thing to be included there. But we still want to build it, so all should probably just include module objects. And I guess we're probably good with that, so let's just try it out. Yep, it builds it, but doesn't link it in. Perfect. So let's put something in this file. I guess we can put, what's the bare minimum thing? We should do a kprintf to make sure that it comes alive. So that would be kernel custodio. And then we should probably have some kind of init function. So maybe like module init. Can look like this. And maybe here we'll just say like the module booted. And then we'll be nice enough to just to do this just for simplicity. Or actually, no, let's not do that. Because this thing is just going to go in the kernel address space and it's going to run, but then we want the kernel to keep going. So I guess this is pretty good. Yeah, so if we can get this to work, then we will have built something very cool. So let's take a look at what symbols this thing now links against. So we have a text segment with a single function, this guy right here, and then we have kprintf externally which is conveniently extern C. I don't know why it's like that, but it simplifies things a little bit at the moment because we don't have to demangle. Or we don't have to mangle or demangle anything. Think about that type of stuff. Because our symbol table, otherwise our symbol table is demangled, as you can see here. So we would need to have mangled names if we wanted to link. But right now we just need to resolve this symbol right here. So let's make a syscall for this. So I guess it would be something like enumerate syscall load module, or module load, let's say. That's pretty good. Module load. Maybe we should also have module unload. And I have no freaking clue how this is going to work, but we'll figure something out. So let's just add the declarations for the syscalls. So we'll say, I guess we can return int, so sys module load and module remove. And when we remove a module, I guess we will remove it by name. So name length. And for module load, maybe we'll do a file name. Path length. That's pretty good, I think. Yeah. Okay, so these, and then, I mean, we're just sketching, right? We'll see how this works out. Process. If not super user, definitely eperm. I'm not going to let normal users do this, but at the same time, just while we are hacking on this, I'm just going to disable this because otherwise it'll get a bit annoying to have to become super user every time. Okay, and then I guess we'll just simplify like this, and then here this is like fix me implement this syscall. Woo. So first things first, let's validate the path. So if validate read path length, then return default. And it's the same story down here actually, so we can just slap that in. All right. So now we want to open this file. So we'll say VFS the open path. Do we need any particular arguments here? I guess no options, no mode, and we want to open it based on the current directory, which, what's it called nowadays? CWD? Current directory? Yeah, that's the one. Process current directory. Why is this italicized? Is this virtual? No. I don't know why italic means here in this context. Anyway. So then if description or error is error, then return description or error. Okay, and then now that we have a description, then we'll say description is this value. Okay, so let's read the whole thing for simplicity. Just say payload. description read entire file. I know, this is just a simple way of doing it, but it's not perfect. And then we are going to want to make an ELF loader, I guess. I forgot how to make this. ELF loader is make ELF loader. Oh, frick. What do we pass to this thing? It's just pointer to the memory. Okay. Const U8. Cool. Payload.data. That's not spooky at all, that this thing doesn't even take any kind of a size. Should probably fix me. ELF loader should really take a size argument as well. Be taking. Okay. So then in ELF loader, we'll call load, because that'll make sure the image is valid. But we don't want to do this part, actually. Oh, maybe we don't want to use ELF loader then. We want to use ELF image. Make ELF image. ELF image. Oh, same story there. So I guess we can say it this way then. If we can't parse it, then we'll return E. What are we even going to say to this? Is there some, like, executable format? Isn't there, what the heck is that called? enoexec? exec format error. Yeah, that's close enough to what I'm looking for. So let's say enoexec. Alright, and then we will say that let's just debug print that we got to this point. Okay, we've loaded the ELF image. Are you happy? Maybe we can iterate over it somehow. ELF image for each symbol. Ooh. Do something like this. Auto symbol. I'm not even really sure what kind of thing we're gonna get here. Symbol dot, no, not gonna tell us. ELF image symbol. Symbol dot, okay, name. Do we have any, what kind of things do we have here? I have to check. We have symbol that gives us by index. Okay, so let's just see what kind of symbols we find in this thing. We'll do it this way, symbol name, at, symbol, value, I guess. Maybe cast that to void star so it comes out as a pointer looking thing. Okay, well, let's just see what this turns into. No match for operator equals. Oh, right, we have to return iteration decision continue. Okay, so let's see what we get here. Oh, I have no way of invoking the syscall. We need a program. What do we call this? Mod load? Module load. Call it. I guess we could call it module load. but it doesn't feel right. Let's call it mod load. That's nicer. I don't know why, it just is. Mod load. This is definitely some serenity.h stuff. So let's see. Module load. Path length. Oh, this is not C++ stuff at all. So again, Dackles and Dackles. Unload, name, and name length. Oakley dokley. I think we're good there. And then here we'll just do module load. I mean, we should be copy pasting this. Yes, sir. Or no, let's just be good boys here and make the syscalls. And let me copy this from somewhere. Load, path length. Name length. And what's wrong with the linkage? C++. Begin Dackles. Am I even in the... Oh, shit. What if we go like that? Everything's good. Okay. Then let's just put it back to kernel mode. Wait, where the heck did I even put those things just now? Oh, crap, these are in modload CPP. Okay, I guess I was thinking I'm putting these in the libc. Because libc should really have Serenity CPP for the Serenity specific stuff. And I really meant to put this in there. I just got confused. So let's just add it to the makefile. Serenity.o, it's all good. Meta and Serenity CPP. Are you confused here? I guess probably it's okay. And was not declared in the scope. Why not? SC module is not declared in that scope. Wait, why would that not work? I wonder if this file is messing it up. It's like this outdated copy. No? Why is this failing? I don't get it. It's right here. look at this, it's red. I haven't actually saved. Oh, that's silly. Okay, so stupid problems behind us. Let's actually implement mod load. So here, I guess we are just going to call module load, and we'll just put it right here, test module.o. We'll do that. Okay, path, strlen of path, nothing super exciting. And then if rc 0 pairs module load. Okay. Now we have to make sure that we actually install the test module. So we'll do cp that. Then we'll have an up-to-date version of the test module and the slash for now. Module unload is not a member of process. Did I forget to... This is module... Oh, I call it remove. Oopsie. Well, I guess we're going to eat another rebuild here. Thankfully, not too many things care about process.h outside of the kernel. Nobody cares about it. But we basically do have to rebuild the whole kernel now. And process CPP as well, of course. Unload. Mwah. Okay, so mod load. And we assert here in elf parse symbol table section index. We don't have one of those apparently, so it gets upset. All right, elf image 109. What does this mean? I haven't looked at elf format for so long. So I guess this looks like we found a symbol table section index when we already have one. What does that mean? Let's look in the file. Test module.o. So we find a sim tab. And we already have one, but I only see one. Is this thing not initialized? No, it's 0 by default. Okay. Why would we find multiple sim tabs? Okay, let's see. Found SHT sim tab, existing one. Existing one is 7, so we find, and then we find, and then we find again. I guess we should print out what the existing, this one is as well here, so. I need to look at how this code works. Also, let's make ourselves a little shortcut for this because I'm already in it. Let's just make it M so that we can get going quickly. Okay, so we found 7 and we have 7. So we should say either it's 0 or assert it's 0 or M symbol table selection index is I. So that seems harmless. Did that not build? I'm confused. $114. Oh, we're here. Stir tab, same problem there. Okay. I mean, we can do the same thing with that. Okay, so what do? We load the ELF image. And here are all the symbols that we find when we iterate over the symbols. So we find module init and kprintf. So this part here, I'm not exactly sure what this was about, but let's just not worry about that right now. But we did load the ELF image, and I'm not happy yet, so I'm not even gonna pretend. So what can we learn more about this symbol? I guess symbol.type, because I bet that's something interesting in there. sttype, it's one of these. Zoom, okay. So the one we're looking for is definitely module init. And I guess 0 is the address of it in the file. So do we also know the size of the symbol? Yes, we do. Okay. So let's see. Symbol type. Size is and then let's also take a look at what else we can iterate over. For each symbol, I had relocations here at some point. I think I deleted it. Yeah. Remove relocation related code since it's not used by the kernel. I think I'm just going to bring it back. I wonder if this patch will just apply as is. Patch. What is RP1? No. Oh, but everything is moved, so it's all different. Okay, well, that's okay. We'll just do this by hand. So let's see, where was that? ELF image. This is right here. Oh, it makes a name to index map. I wonder if we actually need that. Maybe we'll leave this one alone for now. Not sure if we need it. And then this stuff we definitely need, because this is all the iterating over relocation stuff. So ELF image again. This is program header. Oh, it's right here at the end. It's nice and easy. And we just have to do a little bit of text editing. Tap, 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 tap. Okay, and then let's just get rid of support relocations. I think we're going to probably want that name to index map. It's probably going to be useful for us anyway. Then we need this. ELF image is undefined, whatever that is. And we have a whole relocation section class. that I don't remember much about. This was like one of the very first things that I wrote before there was even an operating system. I was working on a little ELF linker, I guess you could say. It'll probably come back to me, I hope. So, because the interesting thing about this module that we're trying to load, right, is that it only has a module in it at offset 0, but obviously we're going to have to load it somewhere in the kernel, so we're going to have to allocate some space for it and put it there and so on. Let's see. Here's some API that I don't love, apparently. For each program header. And stat section name to, what is that, name to section, I guess? Cool. And for each relocation, now we're talking. Let's put that right here. And we'll modernize this with iteration decision break. And now this might be interesting for us. For each relocation, right? I don't know though. We'll see. I'm not really sure what the heck is in this thing anyway. So can we read elf the thing? And what if I want to read elf the relocations, relocks? Okay, so we have some read-only data relocation, and then we have a the kprintf relocation as well. Right. So how do we, and what's actually in this code? Module init. Okay, well, we'll just press forward and see what we can come up with. Elf image case printf has been renamed to just printf. And the rest of it just compiles, I think. It's pretty cool. So let's walk the list of relocations here. Where's for each relocation? I thought I added it. Oh, it's a relocation section thing. Okay, so we'll have to find the section. For each section of type, section header type, what the heck's it called? SHT rel? Wait, is that actually the name of it? Oh, yeah, it is. Okay. Section. Okay, and then section dot relocations for each relocation. Okay, now we're talking. Relocation. Okay, relocation dots. Finally. So maybe we should look at that code that we had there. So basically what we were doing previously was that based on the relocation type we would do something. So 386, there are two types that we handle. 386 PC32, I think that's program counter relative. And then this one is absolute offset. And the ones that we had were these two. So I think these are the ones that we will encounter. Location.type, so we'll probably have to do the same thing here. So what are the names of them? R386 PC32. Isn't that the name of it? That's how it's spelled. Maybe we don't have that defined anymore. PC32. Okay, I don't know where that comes from, so we're just going to grep for it in user include, and hopefully we'll find it somewhere. Seems like it's a 2. And what's the other one? It's a 1. Okay, so we'll just PC32. Do we have these things anywhere? Where are the relocation things? I think this one is from like OpenBSD. Yeah, because didn't want to put a GPL version of ELF header in the system because obviously the system is BSD licensed. So. But it seems like maybe this is missing here. Relocation stuff. Relocation info. RSIM, RType. I'm missing the 386 things, so okay, fine. We're just gonna do this. Cool. Can live with that. So this one is PC relative relocation. And this one is absolute relocation. Okay, and no, not you. Where are you? Here. This one is absolute. Okay, fine. So what do we do with this? Let's print them out, I guess. Location symbol name, and then we'll also do the absolute relocation. I just want to see that we are like iterating over these things properly. And we have to return iteration decision continue here. And I'm probably forgetting something here. What else am I forgetting? Or what code is this? Process 3417. Okay, let's try it. So, what did we get? We loaded the ELF image, and then not a lot of interesting things happened, which is exited. So we did not encounter any relocations, is that it? Relocation section found. Okay, so we found a section at least. That's good. And what were we doing in this code before? I just have to look at how I was iterating this. For each relocation. Oh, maybe I don't need to look in the shtrel specifically. Here we were just looking in the prog bits. That's a bit weird, but then I mean, it's probably not weird, it's just that I don't remember how any of this works. So prog bits are these, and this, and this, and this. So maybe that's what we should be doing. We should be looking in the prog bits, and then relocating whatever is in the prog bits sections. So prog bits then. Because the text segment right here, this one we're interested in relocating because we know we have one in here and we know we have one in the RO data. So we found some relocations here. Yeah. Found an absolute relocation and a PC relative relocation. These are looking kind of goofy here, by the way. Symbol type, symbol name. Oh, maybe I should have a space here. Just for some consistency so that we can see what we're doing. Okay. So this is our super interesting symbol. We definitely want to put that somewhere. I guess we can just put the whole thing somewhere, actually. So let's load this up and put it in some VM. Where do we want to put this? We'll just copy it somewhere, I think, for simplicity. Maybe even put it in a K buffer. Storage, K buffer, create with size, payload.size. Or no, we can create with the exact size. That should be okay. And then, because I think you can have a K buffer with a, yeah, because it still becomes, we still round up the actual backing region to the page size multiple, but yeah, so this is okay. So we'll mem copy everything from the ELF image payload into the storage.data, payload.data, payload.size. And then at this point we can get rid of the payload, so we'll say payload clear. And now we just have the storage here. So okay. So what are we trying to do? We want to, what were we doing here? When we found this, then we had to do a lookup. Right. So we're finding kprintf. So let's special case it for now, so then we don't have to look at the kernel symbol table. And it's an PC relative relocation. So let's see. let's see, U32, symbol address is find kernel symbol, relocation symbol name. And then we will just make a little helper up here for now. String view. Okay. Yeah, like that, and otherwise we will assert not reached. Okay. So do it that way. Okay, and then we have to, I think we have to overwrite it. So what did we do here? I'm just going to cheat and look at my old code. So when we get this one, then we want to patch in, we want to patch in this symbol address into the instruction stream. The relocation information tells us exactly how to patch it in. So that's what we're going to do here. And the way we patch it is, I guess we have a relative offset. I'm just going to copy this. So where, the patch pointer is this. So the patch pointer, this is exactly right. This is the pointer in the instruction stream that we want to replace. So this points directly to what we want to change. And area for section, so we don't care about this because we only have one section, I think. Or let's just do it this way for simplicity for now. Probably, maybe we should, I'm wondering if we should put each section in its own VM allocation or something like that. So that's the symbol address that we're going to use. And then we want to write in the patchy pointer. And this is how we do it. Right. So, oh, what's the target footer? Oh, that's the, right. Okay, so that's the symbol. Okay, so the way this works is the relocation offset tells us exactly where in the instruction stream is there a pointer that we need to reroute somewhere else. And then we set this thing up so that it points directly to that. And then the relative offset is the distance from the place in the instruction stream to the kprintf entry point in this case. So I think this will do it for that. And then I'm thinking now, I'm starting to think, let's make this even simpler for the first attempt here and do a sysget or just outside function. We'll just make a function like this that we can call. Okay, and we'll put it here. And outside func. I'm the outside func. So now we shouldn't even have this absolute relocation. We should only have the single relative relocation. If you look at the relocations, yeah, it's only this one, only the pointer to outside func. So this should be really easy to get going, or not really easy, but couldn't find user region for this. Oh, well, so it's trying to do the patch, but I guess the relocation offset. Oh, right, it needs to be an offset into the storage. Okay, so now let's see. So now let's also have, we're going to need a function pointer to the module init. So we'll say like module init, or no, not like this. Module init function. Damn it, I always forget how function pointers work. I'm so spoiled with C++, I forget how to see syntax for function pointers. Come on, you jerk. Okay, I can just look at create thread or something, I don't know. This is the thing. Why is this so hard to remember? So, go away, Google. We wanted to have one of these. Module init. If symbol name is module init, then module init is going to be, oh, here we need to stir comp. It's going to be the symbol value but we need to cast it to one of these things. Is this how you write this? I hate these. Module init putter module init. And then we can just say module init putter storage data plus symbol value. Okay. And then when we're done with this, we can call freaking module init. I'm gonna say in val, I don't know, something. What? You want an argument? Oh, because I was just copying this. All right, it has no argument. So we definitely crashed. Why is that? Couldn't find a user region for this. So this is a very crappy looking address. Module init is storage data plus symbol value. So what was the symbol value even? It's the outside module init is right here. Value is 0. And that means that module init should be pointing to directly to the start of this piece of code that we had here. So why did that not work out? Storage.data. Storage.data. Let's print out the storage data. So module init found at small value function entry at something like that. We'll see what it says. Function entry at true. Oh, well, dang it. That's not what I wanted. It's that thing that happens in C++ where you your pointer gets cast to a bool rather than a void star. Okay, so the entry is here. So what happens in that function though? I guess I would have assumed that we would just return from it. So let's obj dump examine tell test module O. So module init is right here. And it will just jump to somewhere. So we should see what's there before we execute it then. So do we have some kind of disassembly stuff? No, we don't. Well, let's just be simple and say print out the bytes. And we can even, how many do we need? 1, 2, 3, 4, 5. So module init. Why is my computer sounding so much? It's OBS. Always OBS. Let's see. It's very serious stuff right now, so okay, please let me see the bytes. So what is there? These are the bytes. They don't look super much like the bytes I was expecting. So I was expecting an E9 opcode. Test module.o. Oh, I'm stupid. Okay, so I was just loading the whole file here. This is the start of the ELF. Where is it? 7F. I guess, yeah, it's the start of the ELF, and then we've just patched over this part of it. We need to actually use the section offset here. But I think what we want to do is we want to put each section into its own VM allocation. So let's see. For now, or no, let's just put these in a, we're going to need some kind of structure to hold on to these in the kernel. So loaded module, or module. And then we'll need a k-buffer for them. We're going to need one for each section, really. Maybe we'll remember the name of it. That'll be good. Okay. So, module. Module name is, I don't know. Hello. We'll call it fix me. Okay, now for each section, we're going to do auto section storage is key buffer create with size section dot size. That's nice and simple. And then we'll do module dot sections dot append move section storage. This is just to keep it alive. So I guess we'll do that when we're finished with everything here. So now we want to copy everything into it. So maybe we should use kbuffer copy actually. Copy section raw data, section size. Okay, so my past self has provided us with a pretty pleasant API, I have to admit. Thank you, passengers. So now we're copying the whole section into section storage. And then here we should point into the section storage data. And then likewise up here for each symbol, we should not, we should hold off on this. So we don't know the location of the symbol until we've actually allocated section storage. So I guess we can do that here. If the relocation symbol name is module init, then relocation symbol value. Oh, no, we don't need to say anything about that actually. We'll just store the pointer. And this will be, where are we? Relocation dot offset. Oh no, what the heck am I doing? I want to do this after I've done the relocations, because before the relocations we don't know. Maybe we can do it here. Let's see, section 4. This is a bit tricky. Oh, I see what the problem is, right, because we have to do this afterwards. So we just want to have the pointer to module init, which is going to be in the section storage for let's say we'll have something like a struct. No, we can do this. Hash map string and u8 star section storage for section storage by name. There we go. And then we'll just put these like that. Section storage by name set section dot name. Maybe sections have indices. They don't have indices. Oh, they have names. What were we? Maybe the name is good enough. And we'll just point that to section storage.data. And then we don't need anything else, or do we? Let's not overthink it. So that means that down here we can use the section storage for name by name. Get I guess dot text. Value or null pattern. So here we'll say text base. Text base is this. If text base, turn E and bow. No text section. I'm the outside func. Look at that shit. We're actually calling it. That's awesome. So we loaded a module and executed the code. Okay, so let's see. How would we make this do that printf thing? So now if we try to do this, things are going to get more difficult again. Now this won't work, or it did work. Why did that work? Oh, because we didn't copy in the new module. The test module, we're going to get here and it's going to do nothing, so we have to fix that up. Right, null dereference. So the absolute relocation, I think it works very similarly to the other one, just that you patch in an absolute number instead of a relative number. Yeah, right. So same basic concept. So let's see, that would be auto patch putter. I mean, it's really the same exact concept, right? Oh, the patch pointer is always the same here, right? So this didn't need to be inside of the case. And what is the target putter? Area for section, symbol.section. Okay, so the relocation symbol might be in another section. I guess that's the important part now. And what is this? Okay. So we should probably make a pass here where we allocate all the sections up front. And then we'll make a second pass. Section storage, let's move it like that, and then auto section storage is section storage by name, get section name value or null putter assert section storage. Okay, now we can just use this directly. So the absolute relocation is, we're going to have to find the section that the relocation symbol is in, which means that section containing symbol is section storage containing symbol is section storage by name get value or null putter assert section storage containing symbol, and then patch putter is section storage containing symbol plus relocation symbol value. I think that's basically it. We just have to like that. And up here we have to use an iteration decision. Okay. Test module has booted. We're calling kprintf from the frickin' test module. That's really cool. Let's do a loop here. Kprintf I is now, I don't know, just something to test it out that it works beyond a single call to kprintf. Just a simple sanity test, I guess. Test module has booted over and over and over. See, we still have some things to work out here. So what are we messing up here? We're definitely doing the loop right, but I'm guessing that the relocation goes wrong. So symbol value in both of these cases is 0. The offset is what we're interested in. So I'm doing the value here, but it should be the offset. Symbol has no member name offset. Is that relocation offset? Yeah, okay. It's a little bit weird. We're almost good, but now we're pointing a little awkwardly too far. So how are we messing this up? The relocation offsets. I mean, we're starting a couple of characters into the string. Test module. 1, 2, 3. Starting 3 characters into the string. So I was just thinking that this should be an offset into the section. Section storage containing symbol plus relocation offset. Let's look in the obj dump. So here's the RO data. It's like the strings interpreted as if they were assembly code. So the hex dump would probably be more interesting. So right here we are oh, it's up here actually. Test module has booted, so it's the 6th character here on the line. 54. 54 indeed. But I wonder. I wonder if this somehow doesn't seem right. The relocation offset and the patch pointer, and I'm mixing this thing up here, I think. Because the relocation offset is where the relocation patch should happen, not what we should point to. Right? So, let's see. So this should be the patch point. But these things are also identical other than the offset. So what else is there to a relocation? Let's just go and look at the relocation object, see what's in there. The offset. Offset of relocation, symbol, table index, and type. Oh, This is what we want, the symbol index. Symbol. Right? Or how the heck does how the heck do we know to go to the right freaking absolute offset? I'm confused, so help me out, someone. All right, oracle.com. Calculation. S plus A. I accept your frickin' cookies. Just give me the info. Okay, so PC relative is S plus A minus P. So I'm guessing this is a section base, but you don't explain these anywhere? What's wrong with you? Refer to the explanation following the table. What is the S? S, the value of the symbol whose index resides in the relocation entry. Oh, and what was A? The addend used to compute the value of the relocatable field. So I guess we do have to look at the symbol, even though this is not referring to a symbol, but rather a... I mean, maybe this thing it's like an anonymous symbol or something. I'm not really sure. Like, what do string literals end up as in the ELF binary anyway? I don't know. But they're definitely in this section right here. And it's 25 hex bytes, I guess. At offset 65. So what does the symbol thingy tell us here? Symbol dot value. Let's dump out some more info here then. So absolute relocation, we were printing that already. Absolute relocation, but symbol name was empty. So we'll print out the symbol value. Symbol value. Symbol index. I don't know, I just want to see something, you know? So what is in here? Absolute relocation. In both cases, the absolute relocation has index 5. So it doesn't seem right, because one of the absolute relocations should be different than the other. But they look identical. I am so confused. What happened if you obj dump this thing? So push 0, push 18. Oh shit! There's an offset here. So we shouldn't just overwrite it, we should add to it. Boom. What if we did that? And then, so the offset is already baked into the instruction stream. That's kind of interesting. So, yeah, okay. Aha, perfect. Cool. I'm gonna clean this up a little bit. So I guess we can say if the, or no, we can leave all this debug output actually, because it's probably not going to be very stable anytime soon, this whole thing, but it is pretty cool. So let's add a module file so that we can keep this somewhere. Oh, that's not what I wanted to do. Dang it. And we'll do this as well. Ack string and ack vector and include kernel kbuffer. So module init. Let's see. So we're gonna want to have some kind of storage for these guys. But I guess on init, the init fini, init and fini. That's kind of cute. So where do I want to go? Sys module load, right? I want to include kernel module load. All right. So I'm thinking we're gonna be a little bit hackerly here and just say what are we gonna do? We are just gonna maybe we'll just have a table of modules, map of modules. That's pretty okay, I guess. Static hash map string to ownputter module. All modules. I don't know. It doesn't have to be the most beautiful thing right now. Map is okay. There we go. And then we'll just add this guy to the modules. All modules set module name move module, and module is going to have to move into an ownputter. So do auto module is make module, and the name is fix me for now because that's okay. That's pretty cool. And let's make a procfs thing where we can see all of these. But maybe we'll just build this first, just so we have something to go off. Or I mean commit rather. Is any of this self-contained? I guess the ELF changes. The ELF. Restore the relocation code. I deleted from Git backups. Git backups from Git history. This is going going to be very useful for implementing kernel modules. Damn it. Kernel modules, and we'll also need it for dynamic linking later on. Yeah, okay, so it was kind of silly of me to remove that. It didn't really help anything. And this is kind of a cluster frick of code, but I don't feel terribly bad about it, so let's just verify that it still works after I tweaked it, and then we will just commit it and push forward. So it does not still work. We crash. Wait, why did we crash? Does the module go away? 98. We can't print that it's 99? What? Oh, we go to 99. Oh, okay. So we are here. What are we trying to do here? This is module load. I wonder why it says this. We're clearly not here. I mean, we're clearly in sysmodule load. So we write for operator new. I would assume that we are calling this guy, but why wouldn't that work? I mean, it doesn't actually have to be lazy though. We can, I don't know what's being weird here, but we can do this differently. We can just say, G modules, and then we will just initialize it in process. Oops, process initialize. Although I should probably go somewhere else, but this is as good a place as any at the moment. G modules. Okay, so why are we crashing now? I'm doing something stupid, I just don't know what it is. So crashing at this address. What? Circle. Okay. How the frick? Okay, so it breaks even if I don't call it. What is the stupid thing that I'm doing? What is it? Module. Oh, shit. it's evaluation order. I'm moving it and then dereferencing it at the same time. Can't be doing that, dude. That's a sneaky one. Yeah, there we go. All right, Jesus. Sneaky fucker. Okay. So let's add all of this gunk. Kernel. Implement very basic, very simple kernel module loading. It's now possible to load a .o file into kernel with using via a syscall. Kernel will perform all the necessary ELF relocations and then call module. What is the thing we call module init? In the loaded module. Maybe we should, I feel like it's super ugly the way that we did that root file system thing. So maybe we'll just put the file somewhere where it would look good. I feel like we're not making, like putting it right here is so ugly. What would be a cool place to put this? I feel like we're not making many cool root directories, but at the same time, like, do we really need more? Maybe, would it look bad with a /mod? /mod. It's a little arbitrary. But maybe it's a little arbitrary, but maybe it's okay. Build root file system. Let's just make that directory and live with it. So let's see, mkdir p mod, and we'll get rid of that symlink. It's a bit ugly. And okay, and then in mod load, we'll just say mod test module O. I'm just going to amend this to the previous commit because it got a bit ugly there for a moment. I think this will look quite okay. We'll see when we boot in. So we look at slash, now we have /mod, loop, and mod load. Still loads the module. Very, very cool. Okay. Now, what else do we want to do here? Let's see if we can unload the module. Void module fini. Okay, printf test module is being removed. Frick. Okay, I guess that, and then we'll say bye-bye. So when you remove one, we should just look it up, first of all, by name. Well, right now the name is fixme, so I guess we'll have to remove it by that name. Let's see. Auto. What do we have? Auto it is g modules find name. Probably when we should probably store the init function and the fini thingy together with the module instead. So we'll put these here. Yep. And then module. Okay, and yeah, so let's also cache the module Finny player. Else Finny and Finny. Okay, so then if it is G modules and return E search, I guess. I don't know. eSearch not found. We could do enoent. No search file or directory. I guess that's pretty okay. And then it value module Finny. If there is a module Finny, we'll call it. And then we will remove the module. G modules remove it. Boom. That's pretty cool. But maybe we should write it this way actually. It's an interrupt disabler. Or, well, I feel like you shouldn't be allowed to mess with this thing if... Okay, let's worry about that later. I was thinking about like locking the module table and everything, but let's just get the basic stuff working instead and not think too much about synchronizing everything. Famous last words. Famous words last, perhaps. So now we're going to need a user land program for this as well. We have mod load, and we'll need mod unload, I guess. Mod unload CP meta sr mod unload. And right now, let's just do this. Module unload name. It's very simple, but maybe it would work. Wouldn't that be awesome? So mod load. I have loaded this thingy, hopefully, and mod unload. Test module is being removed. Holy shit. And then mod unload again. No such file or directory. Dude, it works. That's fucking cool. Alright. Okay, so what do we have now? Kernel. Implement basic module. Unloading. Kernel modules can now be unloaded via a syscall. Before they get one last chance, they get a chance to run some code, of course. Before deallocating them, we call mod module Finny symbol. Cool. Now let's put something in the procfs so we can see the modules. I think we'll just call it proc modules. I'll just put it next to these guys. So this would be modules, and then proc file system is kind of weird, but you should only have to edit those two places. Oh yeah, I have to actually implement that file as well. So modules, this is the way you implement a file in the proc file system. You add it to the table that we just did, and then you create this callback function that generates a K buffer with the contents of the file. It's pretty straightforward. So here we are just gonna say for now extern hash map string to ownputter module g modules, and we'll need kernel module. All right, and then we will just think. I guess we should make JSON here actually. So this would be a JSON array serializer. Okay, I need some help. This is how you do it. Yeah, right. So we want to iterate over G modules. And then add an object to each one, and the name is going to be the name, and module init. We can put these in here, pointers to these functions. Fini. I think we'll just put this as a U32, basically. And then anyone looking at this JSON, they're going to have to understand that that's a pointer and make sense of it whatever way they want. And I guess then we just need to do array finish, and we should be good. So proc modules is just an empty array, but if we mod load, then it has our module in it. That's pretty awesome. And then, of course, that's how you would know that there's a module that you could remove. Yeah. It's so neat. Snap out of it. Okay. Kernel add proc modules. A simple window into the add proc modules to expose the loaded modules to user space. To enumerate the currently added modules. Yeah. Pretty cool. What if we wanted to call something other than kprintf though? Let's see, process cpp, because now this is hard coded here, right? And we don't need the outside func, but it would be cool if we could find any symbol. And we do have the kernel map, and we do load this when we run, but it is demangled here, so we're going to have to not demangle the names first of all. So we'll just remove the C argument here. Okay, map. Now the kernel map will have proper looking names for us. And then ksims. So we should be able to write a function that gives us an address for a name. We just need the backwards version of this. So U32, address for ksim. Kernel symbol. Here we go. Const char name. And doesn't have to be anything fancy at all. We'll just walk all of our ksims. Say if strcomp name sksyms I dot name return sksyms I dot address. What's actually there? I forget what's in there. Dot address. Right? Expected paren. Oh, my bad. Sorry. Okay, there we go. Then we'll just return find kernel symbol. Address for kernel symbol. Okay. And I wonder if this would just work. That would be fascinating. Let's see, test object. Test module, sorry. Let's do something here that we didn't know how to do before. So, call sys getGit. Saying git is current process. I would think that this should work now. And then we'll print the current git. Or no, we'll print the current UID. Yeah, let's just print the UID. What am I even thinking? Current UID is D. Or maybe we can even print the current process, current thread. Okay, I don't know why I keep doing this. Current process name. Okay, so process name characters. Will it be able to find all of this stuff? I wonder. Current PID. Let's do this one as well. Current process sys get PID. Okay, so now how does test module look? We got all this stuff here looking like this. So this definitely broke down. We don't have section storage containing a symbol for the name current. Wait, why is that? Sys module load. Section storage containing symbol at 3437. So we are here. We're hitting this absolute relocation. Current. wonder what that, we're looking at this name right here, this section name, so section name. Because kprintf we can evidently find. Oh, okay. Absolute relocation. Wait. Absolute relocation, we shouldn't just look in the own file. It's an external symbol. So it's not in the file. That has to be different somehow. Current. It has to tell us that the symbol type is different somehow, right? SD type. Wait, what am I looking for? The info. I mean, the info here is interesting, right? Like there's 9 here. Nothing else has the 9 on it. So I'm thinking that that's relevant. Symbol table info. Type and binding attributes. Local symbol, global. Wait, so I want to look in syself.h, I guess. Okay, just where is it? Where is it, damn it? st info. Wait, so, damn it. How do I read that? ELF. Which part is which? The info is, the bind is info, shifted up 4. So it's not, that's this. This is the bind. Or it's this, actually. And this is the type. And wait, what? Info and F. So this is a type. And what were they saying with bind then? So bind is 50 hex? Why? My brain is not computing. So this is for constructing the info based on bind and type. Okay. Shift 4 to, but these are 8 bits. So if you shift 4, then you, I don't understand. Then what is that 9? ST info. Oh, it's a very small field. Oh wait, are they expanding this somehow here? These are not symbols, are they? These are relocations. Oh, I'm such a dumbass. Okay. That's why it doesn't make any sense. So then what do they mean then? Vim user include elf. The relocation info. Tell me more about your relocation info, dude. Relocation type and symbol index. Relocation type. So this is a different relocation type. What is this type? So this is the type. Oh, dude, why am I so slow in the head? So it's just the index? Okay, fine. Symbol name current. But then how do we know where to find the symbol? The symbol type is different. Okay, so I'm catching up with my past self, because apparently my past self was thinking ahead. It's just that I'm getting myself confused. Okay, so the relocation points to the simple current, and the symbol current, which we should be able to find it. Current is global, not local. That seems like the important part. So the bind for this is global. So how do we find that out? Symbol. Type. Oh, we don't have a bind getter. Okay, so then let's say unsigned bind const return this guy right here. Return the bind information for the symbol. Okay, now where we're looking this up. So we don't want to use the section storage unless it's a local. So if relocation symbol bind is elf, oh damn it, what's this thing even called? Local, STB local, right? Obvious. Then that's the game. Else if relocation symbol bind global else assert not reached, for crying out loud. So what we're going to patch in here then is the address to this mother fricker. So the value of this symbol is 0, so it's useless to us. But instead, we want to find the address for kernel symbol. Relocation symbol name. Okay, I think that's it. Loadable. Module has booted, current bit 15, current processing modload. Oof. Awesome, dude. So cool. So now we have successfully runtime linked against kernel symbols. How cool is that? Of course, now our kernel backtraces look broken because they were expecting the kernel map file to be demangled, but we can fix that. We can just demangle on demand in the kernel. But this is super cool, dude. So let's just commit this. Commit live elf, add elf image symbol bind. Yeah. And then the rest. Kernel. Allow modules to link against anything in kernel map. We now use ksims from kernel map, symbols from kernel map to perform to link modules as they are loaded into the kernel. This is pretty freaking cool. And let's just fix those back traces there so that we demangle the names. We can just call the, there's this ABI function for that we can just use. So, okay, symbolicate. Where do we use that? I guess this is where we do the name, right? And likewise up here, okay. This is a little bit annoying. Okay, I'm too tired to deal with fixing the symbolication of kernel symbols right now, or the demangling rather. So I'm just gonna quit while I'm ahead, and just enjoy the fact that we can now load kernel modules and we can unload them. And obviously it's still hard-coded which path it uses, and the name is still fix me and everything, but this is some insanely good progress, I would say. Load. Boom. If we try to load it again, what happens? Oof, it's by name. Oof, oof. Oh, well, I guess we just leaked a little bit there. So, a lot of things to still fix, but dude, very cool. We have the start of modules. This will make it a lot easier in the future to develop optional functionality and prototype stuff, because you'll be able to work on something even inside Serenity now for the kernel, and then you can load it, see how it works, and then unload it, and do it over again, change stuff, load it again, you know. It's really going to help development, I think. So very, very exciting stuff. So this is going to be the end of today's video. So if you made it this far, then I thank you for watching, for sticking it out with me. I hope you saw something interesting here. Certainly we saw a lot of ELF internals, and but basically this was, at least for me, super interesting. So yeah, I don't know what to say. I'm just excited about this, I guess. So thanks for hanging out. I'll see you guys next time. Bye.